What we're going to look at here in this video is a special operation involving two vectors, which we're going to call the vector product. Now, we've already looked at combining any two vectors in three-dimensional space to produce a scalar using the scalar product, so a dot product, as we also called it. Now, it's also possible to combine an operation where we can multiply two vectors A and B together to produce a vector solution rather than a scalar solution. This is referred to as what's called the vector product or cross product, given that it's denoted by this here, A cross B. Now, what we have to be able to do is understand, one, how to do this, and two, what it actually means for us in our three-dimensional system. Now, if we think in three dimensions, if we take any two non-parallel vectors, let's say A and B, we can use them to define a plane. Within that system, what we're going to do is take a vector which we're going to call n. We're going to call that the normal to the plane, and it's going to be a unit vector perpendicular to this plane. What that means is I now have a right-handed system involving those three vectors, where I've got vector A representing one direction, vector B representing another, and the normal representing what would be the z-axis and being parallel to the plane itself, so that we've got that system there. Now, what this allows us to do is set up a plane so that we can define the cross product, and we're able to then look at how we calculate it and what it physically means within the system. Essentially, the way to remember it is when we multiply two vectors A and B together and do the cross product or vector product, it tells us what this normal vector is that is perpendicular to the plane. That's what we're ultimately going to look at. But first, we can look at a definition of the vector product where we incorporate the magnitudes of the vectors A and B and the normal vector n, as well as the angle between the two vectors itself. Now, we know that the vector product is defined by this A cross B notation here. Now, what I'm going to tell you is that one way of defining the vector product is by saying A cross B equals n times the magnitude of A, magnitude of B, sine theta, where theta is the angle between the positive directions of A and B. Now, that n still represents the unit vector perpendicular to the plane, so a normal vector there. What this will give me is a normal vector times some scalar here which comes from the vectors A and B. So ultimately, we'll actually end up with an answer that is a vector itself. It's just going to be some scalar multiple of this unit vector normal to the plane. So we need to be able to work with this and do it. And there's a few properties we have to know about this and calculate before we can physically get onto using components of vectors in order to be able to calculate the cross product of two of them and tell each other what this normal vector is. Now, first thing I want you to take into account is that because we've said we can't have two parallel vectors, we can't define a plane with it. Well, similarly, if either A or B are 0, our normal to the plane is not defined. So what we say at that point is that a cross product, A cross B, that is defined as 0. So that gives me a situation where I've not got a plane, because I've not got two vectors, two distinct vectors, A and B, such that I can calculate the normal. However, if we ignore that, let's say A and B are non-zero for the rest of the definitions we're going to look at. A few key characteristics. First thing being that A cross B, so our vector product of A and B, gives us a vector as we've mentioned, and it's with the same sense and direction as the normal vector n. So basically, it gives us, as I mentioned before, a vector perpendicular to the plane containing A and B. Second thing is that if we take the magnitude of this vector A cross B that we get, that's the equivalent of the magnitude of A, magnitude of B, sine theta. Now, this comes from the fact that we're taking the magnitude of this relationship here, but we've already said that n, or normal to the plane, is a unit vector. Magnitude of a unit vector is 1, so it's going to be 1 times all of this, so we then whittle it down to just magnitude A, magnitude B, sine theta. Now, if we take two vectors that are parallel or similar to each other, so A cross A, or A cross KA, so some scalar multiple of the vector A. If we were to do that, what we'd find is that the magnitude of these vectors, so the magnitude of A cross A, would be magnitude of A, magnitude of B, sine theta. Now sine theta in this case would be 0. There's no angle between two vectors that are the same or that are parallel to one another and just scalar multiples of each other. So our cross product, the magnitude of it, would be 0. So we physically wouldn't have a normal to the plane because the plane would be defined by two vectors that are parallel or the same to one another. We can't define a plane in three-dimensional space. Next rule I want you to remember is if A and B are non-zero, but we then calculate our cross product and we get an answer of 0 in that case, then A and B are parallel. So what that tells us is that we don't have a plane in three-dimensional space because we don't have a cross product, a vector product, that we can calculate and define to give us a normal to that plane. So two parallel vectors, we can't define a three-dimensional plane because of it. Next thing I want you to remember is the vector product is non-commutative. So in this case, A cross B does not equal B cross A, it actually equals negative B cross A. So it's not the same in terms of the scalar product when it comes to that. That's one that trips a few folk up. You have to bear that in mind. It's not commutative, so that doesn't work. However, if you look at this last point here, it's still distributive over addition. So if we were to take A cross of the vectors B plus C, that would be the equivalent of doing A cross B plus A cross C. Similarly, if we were to do A plus B and then take the cross product with C, that would be the same as doing A cross C plus B cross C. So it is distributive over addition, it's just not commutative in terms of being able to swap the vectors round. I'll show you why in just a second, but the way to remember it is essentially it changes the direction of our normal to point the opposite way. Last thing I want you to think about is that if we take the unit vectors in our right-handed system, so the I, the j and the k, and we use the formula that's above, so this one here right at the very start, where we define A cross B as being n times the magnitude of A, magnitude of B sine theta. For each of these, remember that they're unit vectors, so the magnitude is going to be 1, and the angle between each of them is 90 degrees, because they're perpendicular to each of them. So what we'll find is I cross j is k, j cross k is I, and k cross I is j. However, because we know it's not commutative, if we were to switch the order of them around, our j cross I would be negative k, our k cross j would be negative I, and our I cross k would be negative j. So think of it as if you went x to y, y to z, z to x. They would all be positive answers, but if you went the other way around, counterclockwise around your system if you like, and went x to z, z to y, y to x, they would all be negative. You'd just be changing the direction that you work your way through the system. These are the key things you need to remember when it comes to the vector product. We have to know each of these, we have to remember them, recall them, and be able to use them within any scenario where we have to calculate this characteristic of two vectors. Now, one thing I want to look at is an example where we look at this, where I can show you that two vectors are not commutative and why this is the case. Let's imagine I'm going to look at a three-dimensional system I've got here. So I've got two vectors, A and B, and I'm going to tell you that the vector A is this way and it's got a magnitude of √3. Vector B points this direction with a magnitude of 3, and the angle between the two vectors here is 60 degrees. So what I've now got essentially is, if you wanted to think about it in this way, I've got a plane that is defined by both of those vectors in 3 dimensions, and this bit here, the point where those two vectors meet, I've got a normal to the plane which is perpendicular to both of those vectors. So I've defined my system using that. Now if we were to look at A cross B, we know that that would be equal to n times the magnitude of A, magnitude of B, sine theta. So in this case, that would be A cross B, so it would be n times the magnitude of A, which is √3, times the magnitude of B, which is 3, times sine theta, so times sine 60 degrees. So in this case, I'd have a cross b equals, well, it's going to be my normal vector times this scalar here. So I've got root 3 times 3. Sine 60 is root 3 over 2. So I'd get root 3 squared, which is 3, times 3 over 2. So I'd get 9 over 2 times n. Now if I were to take the magnitude of it, so the magnitude of a cross b, that would quite simply give 9 over 2. Because I could just drop the n off here. The magnitude of this bit is just 1. So I'd be left with this. Now because I'm doing the cross product of a and b, if we were to think about a right-handed system and put our hand out, your index finger, pointing out in this case, represents the vector a. Your finger pointing to the left in the system represents your vector b. Now your third finger, your thumb, represents the normal. Now if you look at your hand, when you've done that, you'll notice that your thumb points up the way. So the sense and direction of that vector, the normal vector to that plane where we do a cross b, is positive. It's pointing up the way, it's going in a positive direction with a positive sense. Let's imagine we then look at b cross a. So the other direction there. So let's look at b cross a. Similarly, that's going to be given by n times the magnitude of b, magnitude of a sine theta. And we can plug in the exact same values and take the magnitude. So in this case, we get magnitude of b cross a, again, would give me 9 over 2. Now, you're looking at it and wondering why that's the case. I told you that it wasn't commutative. However, if you then take a right-handed system for this one, what you'll notice is that your index finger will represent the b, the first vector, which is pointing away from you, and your finger that points to the left represents your vector a. It's opposite orientation to the other system. Your thumb pointing up the way will still represent the normal. If I were to take my hand, so I could make it the same as my right-handed system for the a cross b, I'd have to turn it upside down, and then my fingers would represent the same vectors, the a and the b, in the plane that I defined at the start. The only difference is my normal n would point down the way. So what I've got here is, yes, they've got the same magnitude, which is expected. The only difference is my b cross a is now a vector with a different direction, so the opposite direction to the vector a cross b. So my vector a cross b essentially will be given by 9 over 2 times n, but this one here, because it's going the opposite direction, it's got the opposite sense, I'd have to say that my b cross a in this case would be negative 9 over 2 times my normal n. And it all comes from that orientation. You can use your hand. You might think to yourself, I'm looking a wee bit silly doing this in the exam, sitting holding your hand out like this. But if you use that, what you've got to do is remember to represent your index as your first vector, pointing left is your second, your thumb is your normal, and it'll tell you which direction your thumb points to then represent your system. And that'll tell you where your normal goes. And this just goes to show why a cross b and b cross a become the opposite of each other. So this just tells me why a cross b is equal to the negative of b cross a. It's all got to do with the orientation of our system because of the vectors and the way that we're taking them, and the fact that when we switch them round, a normal points in the opposite direction and has the opposite sense to each other. That's where this all comes from. So using these relationships, so taking the vector product, the cross product, we're able to use this information here, given the magnitude of vectors and an angle between them, in order to be able to calculate properties like this normal vector, and then the magnitude of those vectors. So what's the size of this normal vector, and what does it look like? However, this isn't always going to be the case. We have to be able to do this in terms of components of vectors. So if we're given an I, J and K, and I say to you, right, I want to know the normal to the plane with those two vectors, you have to be able to do it. If you want to know how to do that, which is something that's vital, this is when we need to move on to the cross product using component vectors. And I'll leave you to look at that just now.